Welcome to the Explainer. Okay, let's jump right in. Quantum computing is no longer just some sci-fi concept confined to university physics departments. As we sit here right now in 2026, it is a rapidly approaching reality that's fundamentally rewriting the rules of what's computationally possible. Today, we're looking at the quantum ticking clock, and honestly, the stakes could not be higher. To really wrap your head around just how massive this technological shift is, I want you to consider a truly incomprehensible number: 10 septillion years. That's a 1 followed by 25 zeros. And that is exactly how long it would take one of today's absolute fastest, top-of-the-line classical supercomputers to complete one specific, immensely complex calculation. To put that into perspective, that duration is vastly longer than the universe has even existed.
But here's the mind-bending contrast. In December 2024, Google's Willow chip solved that exact same problem in under 5 minutes. Yeah, under 5 minutes. We aren't just talking about making your smartphone load a web page a little bit faster. We are talking about solving the practically impossible. It's the ultimate proof of an unimaginable leap in processing power.
So, to make sense of all this, here is our roadmap for today's Explainer. Section 1, Beyond Classical Computing. Section 2, The Race for Perfect Qubits. Section 3, The Existential Cryptography Threat. Section 4, Solving the Impossible. And finally, Section 5, The Global Quantum Race.
All right, Section 1, Beyond Classical Computing. Let's look at how this actually works.
To understand the future here, we gotta look at the physics. Classical computers run on binary bits, right? Zeros and ones. It's kind of like a coin lying flat on the table. It's either heads or it's tails. But the quantum realm plays by totally different rules. It operates on this principle called superposition. A quantum bit, or qubit, is more like a spinning coin. While it's spinning, it exists in a state of both 0 and 1 simultaneously until you measure it. Because of this, just 50 qubits can represent over quadrillion states at the exact same time. It's wild.
And honestly, it gets even stranger. This brings us to entanglement. Albert Einstein famously called this spooky action at a distance. When qubits become entangled, their states are instantaneously correlated, no matter how far apart they physically are. In a quantum computer, this entanglement links qubits so that whatever you do to one affects the others in a highly coordinated way. This spooky coordination is the actual engine behind the immense processing power we're seeing. Section 2, The Race for Perfect Qubits. So how do you actually build one of these things? Well, there isn't just one settled way yet. Several different methods, or modalities, are battling it out right now in a really high-stakes hardware war. We've got superconducting qubits, favored by IBM and Google. They're lightning fast, but they require freezing temperatures, like around 15 millikelvin. Then you have trapped ion systems, used by companies like IonQ. These are highly stable, but a bit slower. And then there are neutral atom platforms. What's super fascinating here is that in March 2026, Google made a huge surprising pivot to launch a parallel neutral atom research program, which is a massive industry endorsement of its scalability and flexibility. But regardless of the hardware type, they all face one grand challenge, and that's the decoherence problem. Qubits are extraordinarily fragile. A single stray photon, a tiny vibration, or even a microscopic fluctuation in temperature can completely destroy their quantum state. They are literally the ultimate divas of the physics world. So the absolute key is error correction. And this is exactly why Google's Willow chip was such a historic milestone back in 2024. It achieved below threshold exponential error reduction. Simply put, as they added more physical parts to the system, it actually got quieter and more reliable rather than noisier. That's a real game changer. Section 3, The Existential Cryptography Threat. With this hardware maturing so fast, we need to pivot sharply to the immediate stakes. Almost all of the internet's security rests on the assumed difficulty of factoring massive numbers. But there's this thing called Shor's algorithm. It's a specific mathematical formula that allows a quantum computer to factor these large integers exponentially faster. A fault-tolerant quantum computer running Shor's algorithm will completely break modern RSA and ECC encryption. It literally renders the mathematical foundation of HTTPS, your banking, and even classified government communications totally obsolete.
Now, you might be thinking, well, fault-tolerant machines are still years away, so my data is safe for now. Unfortunately, no. This brings us to a concept known as harvest now, decrypt later, or HNDL. This is the immediate threat, where adversaries intercept and store your currently encrypted data so they can decrypt it once those future computers finally arrive. For data that needs to stay confidential for decades, think medical records, long-term contracts, or classified intelligence, the quantum threat is effectively already here. Let's just walk step by step through the terrifyingly simple logistics of an HNDL attack. Step 1. Bad actors intercept encrypted data today over public networks. Step 2. They store it in massive, cheap data centers. And Step 3. They simply wait. Once a fault-tolerant quantum machine is operational, they decrypt your data. It is a highly patient and incredibly effective strategy. Luckily, we aren't just sitting ducks. The defense rollout is already underway. Back in August 2024, NIST released its finalized post-quantum cryptography standards. These are new algorithms, like ML-Chem, that don't rely on easily broken factoring. By 2027, the HQC backup standard is going to be finalized. And looking ahead to 2035, quantum vulnerable algorithms have to be entirely removed from federal systems. It's a massive global defense overhaul, essentially fighting the ticking clock. Section 4, Solving the Impossible. Okay, take a breath. It is crucial to remember that quantum computing isn't just some impending threat we have to mitigate. It holds incredibly positive applications for human progress. See, quantum computers are natural simulators for nature because nature operates on quantum mechanics. For example, in drug discovery, Google's Quantum Echoes algorithm recently modeled a 28-atom molecule, revealing information traditional methods just couldn't see. We also have material science poised to discover new clean energy batteries. In finance, massive portfolio optimization is being tested. And over in medical device simulation, IonQ hit a major 2025 milestone by actually outperforming classical high-performance computing by 12%. And finally, Section 5, the global quantum race. The power to natively simulate nature, combined with the ability to break global encryption, makes this technology a matter of ultimate national security and immense economic value. Currently, North America dominates the global market share with 61%, and there's been an absolute explosion of private venture capital. We're talking nearly $5 billion deployed in 2025 alone. That is a massive 192% increase from the previous year. Plus, experts are anticipating a huge IPO pipeline plan for 2026. The economic stakes here are just astronomical. But it's not just private capital. Governments are rapidly racing for tech sovereignty to avoid a catastrophic Q-Day scenario. The numbers here are staggering. The US saw $12.7 billion in global government commitments in 2025. China has committed upwards of $15 billion. Over in Europe, they're actively building a pan-European quantum internet alliance. And India inaugurated the Amaravati open access testbeds in April 2026. Every single major power is heavily invested in this race. However, there is a critical bottleneck in this entire revolution, and it's the talent crisis. Over 250,000 new quantum professionals are going to be needed globally by 2030, but today, there is only one qualified candidate for every 3 open positions. We desperately lack the highly specialized physicists, the cryogenic engineers, and the quantum software developers required to actually build and program these systems. Which leaves us with a pretty profound question to ponder as we wrap up today's explainer. As we speed towards Q-Day, is this immense, almost unfathomable power going to democratize human progress? Will it accelerate cures for diseases and help fix our climate? Or will it concentrate ultimate computational control into the hands of a very select few? Some researchers, looking at the sheer impossibility of this computing power, even suggest it mathematically taps into multiple parallel universes. Whether you buy into the multiverse theory or not, one thing is absolutely certain: the quantum clock is ticking. So, what do you think our quantum future holds?